to read chapter 1, measurement and uncertainties. So unit 1.1, measurement in physics. Physics is an experimental science in which measurements made must be expressed in units. So like, what is physics? Physics is just the experimental science that we can do practically, and a sort of thing like we can just imagine like physical and like doing experiments. So, and then in the international system of units used throughout this book, the SI system, there are 7 fundamental units which we are going to read now, which are defined in this section. All quantities are expressed in terms of these units directly or as a combination of them. And the SI system has 7 fundamental units, and it is quite amazing that only 7 are required. These are the meter denoted by M. The I think everyone knows what is meter. And this is the unit of distance. It is the distance traveled by light in a vacuum in a time of these this much seconds. And the next is the kilogram, which is denoted by kg. This is the unit of mass. It is the mass of a certain quantity of a platinum iridium alloy kept at Bureau International des Ports at Monsieur E. France. So kilogram kg, it's a unit of mass. If we have to like measure mass, so we use this unit, which is kilogram. Everyone knows. And then the second, this is the unit of time denoted by s. A second is the duration of 9,192,631,770 full oscillations of the electromagnetic radiation emitted in a transition between the two hyperfine energy levels in the ground state of cesium 133 atom. Okay, and so the next is ampere, which is denoted by A. This is the unit of electric current. It is defined as the current that the current which, when flowing in two parallel conductors 1 meter apart, produces a force of 2 into 10 raised to power 7 Newton. N is capital N denotes Newton on the length of 1 meter of conductor. So remember ampere. Ampere is the unit of electric current. Okay, and then next comes Kelvin, which is denoted by K. This is the unit of temperature. It is 1 over 273.16 of the thermodynamic temperature of the triple point of water. We will be learning this triple point of water and the thermodynamic temperature in the next upcoming lessons. So just and yeah, the next is the mole, which is denoted by MOL, mole. 1 mole of a substance contains as many particles as there are atoms in 12 gram of carbon 12. This special number of particle is called Avogadro's number and is approximately 6.02 into 10 raised to power 27. 6.02 into 10 raised to power 23 is the Avogadro's number, and we have to remember this number. And the candela CD, this is unit of luminous intensity. It is the intensity of the source of frequency 5.40 into 10 raised to power 14 hertz, emitting 1 over 683 watt per steradian. So I think we will not use candela as much often as, yeah. So you do not need to memorize the details of these definitions. Yeah, in this book we will use all the basic units except the last one. Physical quantities other than those above the units that are combination of the 7 fundamental units. They have derived units. Okay, for example, speed has unit of distance over time, and distance over time, so it's meters per second denoted by meter per second, or preferably this one. And acceleration has units of meters per second squared. Yeah, meter per second squared, like a power of 2, and which can also be denoted by this ms raised to power minus 2. And the unit of force is Newton, as I have mentioned before. It equals the combination kg ms minus 2, like kilogram meter per second squared. Yeah. Energy, a very important quantity in physics, has the joule, J, as its unit. The joule is the combination of nm. Nm is Newton meter. As everyone know, n is Newton, so it is Newton meter, and it also equals to kg ms raised to the power minus 2 meter. It's how I remember. And um, the quantity power has units of energy per unit of time, and so is measured in joules per second. This combination is called watt. So remember, the whole combination is also known as watt, and 1 watt is Newton meter per second, and which also equals 1 kg ms raised to power minus 2 ms minus 1, and so metric multipliers. Let's see. Small or large quantities can be expressed in terms of units that are related to the basic ones by powers of 10. Thus, a nanometer nm is 10 to the power minus 9 meter, and a microgram, which is denoted by this symbol, this is known as mu, and g is gram, is 10 to the power minus 6 gram, which equals 10 to the power minus 9 kg. And minus 9, you can imagine how small it is. Minus 9, 10 to the power minus 9. And the next is the giga electron volt, GeV, which equals to 10 to the power 9 electron volt. ev is electron volt. So the most common prefixes are given in this table below. So let's have a look here. So here are the powers given and the prefixes, the symbols, all the symbols. That's okay. Let's read. So 10 to the power 18 minus 18. The prefix is used is etto. Symbol is capital A, and 10 to the power minus 15 is femto, which is denoted by capital F, like the bigger letter F. And 10 to the power minus 12 is pico, which is denoted by small p, and 10 to the power minus 9 is nano, which is denoted by small n. 10 to the power minus 6 is micro, denoted by this symbol mu. 10 to the power minus 3 is milli, which is denoted by small m, and 10 to the power minus 2 is centi, denoted by small c, and 10 to the power minus 1 is deci, or many people say deci, is d. And next row, next column, sorry, so is 10 to the power 1 is deca, denoted by symbol da. 10 to the power 2 is hecto, denoted by capital H or small h, and 10 to the power 3 is kilo, denoted by small k, and 10 to the power 6 is mega, capital M. 10 to the power 9 is giga, is g. Some people say it giga, and but I say it giga. 10 to the power 12 is tera, denoted by capital T. 10 to the power 15 is peta, is p, and 10 to the power 18 is exa, capital E. So we have to learn all this table. Okay, so let's move on. Orders of magnitude and estimates. Expressing a quantity as a plane power of 10 gives what is called the order of magnitude of that quantity. Thus, the mass of the universe has an order of magnitude of 53 kg is kilogram, right? So mass of the universe has the order of magnitude of 10 to the power 53 kilogram. We can imagine how big is it is. And the mass of the Milky Way galaxy has an order of magnitude of 10 to the power 41 kilogram. It's quite huge. And the ratio of the two mass is then simply 10 to the power 12. We can simply see that. And here comes our next table. So it's like it gives example of the distance, masses, and times, and given as order of magnitude. So distance to edge of observable universe, which is length. uh, Length is measured in meters. Okay, so 10 raised power 26 meter, and distance over to the Andromeda galaxy is 10 raised power 22. Diameter of the Milky Way galaxy is 10 raised power 21, and distance to the nearest star is 10 raised power 16, and diameter of the solar system is 10 raised power 13. Distance to the sun is 10 raised power 11. Radius of the earth is 10 raised power 7. Size of the cell is 10 raised power minus 5. This is not that cell or batteries, some people say. This is the cell we have in biology, that cell which is the smallest component of life, by which we all the human beings are made up of. So okay, this is not the one is which is composed of electricity one. So size of the hydrogen atom is 10 raised power minus 10. Size of an A equals 50 nucleus is 10 raised power minus 15. So we can imagine like nucleus is too small and is embedded in the cell, is 10 raised power minus 15. And the size of the proton is a positively charged particle that we are going to learn in the next upcoming lessons. So it is 10 raised power minus 15, and the Planck length is 10 raised power minus 35 meter. Okay, these were some interesting distances. Okay, let's move on. The universe, now here comes the mass kilogram. Okay, universe, it has the mass of 10 raised power 53 kilograms. The Milky Way galaxy has mass of 10 raised power 41 kilograms. The sun has mass of 10 raised power 30 kilograms, and the earth has mass of 10 raised power 24 kilograms. And the Boeing 747, do you guys know what is this Boeing 747? Yes, this is the aircraft, the Boeing 747, which is quite huge, and so its mass is 10 raised power 5, which is empty. And if it has passengers and the rest of the crew members in it, and along with the luggage, then I don't know how huge the mass will be. Because the one thing I would tell, that the aircraft's entire body is made up of the metals that are like in lightweight, so that the aircrafts, all the airplanes and the aircrafts, they can fly easily and take off easily. So that's why. So the next is an apple, which has mass of 0.2 kg, and the raindrop has 10 raised power minus 6 kg. A bacterium is 10 raised power minus 15 kg, and smallest virus is 10 raised power minus 21 kilogram. A hydrogen atom is 10 raised power minus 27 kilogram, and an electron is 10 raised power minus 30 kilogram. So here comes some interesting times in seconds. Age of universe is 10 raised power 17, and age of the earth is 10 raised power 17. Time of the travel by light to the nearby star is 10 raised power 8, and 1 year is 10 raised power 7. 1 day, the time is 10 raised power 5, and the period of a heartbeat is 1 second. One heartbeat takes place in 1 second, so mm, quite interesting. Lifetime of a pion is 10 raised power minus 8, and lifetime of omega particle is 10 raised power minus 10 seconds, and the time of passage of light across a proton is 10 raised power minus 24 seconds. Okay, so let's see some interesting examples here. So estimate how many grains of sand are required to fill the volume of the earth. This is a classic problem that goes back to Aristotle. The radius of the earth is about 6 into 10 raised power 6 meter. Hmm. So we have to estimate, like find out how many grains of sand are required to fill the volume of earth. I would ask everyone to please don't look at the solution and try by yourself, and just I will wait for 5 seconds. Maybe you can pause the video and then try to solve it. Okay, then let's see the solution. The volume of the earth is 4 by 3 pi r cube. Like earth is a sphere, so its volume will be 4 by 3 pi r cube, and then we will calculate all these by putting on the values. We will get 10 raised to power 21 meter cube. The diameter of the grain of sand varies, of course, but we will take 1 millimeters as a fair estimate. The volume of a grain of sand is about 1 into 10 raised to power minus 3, and the whole power is 3 meter cube. Then the number of grain of sand required to fill the earth is 10 raised to power 21 over 1 into 10 raised to power minus 3, and the whole power is 3, which is approximately 10 raised to power 30. And then here comes the next problem. And so the question is, estimate the speed with which human hair grows. Quite interesting question. Let's see the solution. I have my hair cut every 2 months, and the barber cuts a length of about 2 centimeter, just 2 centimeter. The speed is therefore 2 into 10 raised by minus 2 over 2 into 30 into 24 into 60 into 60 meter over second. And so it's approximately this. When we will calculate on the values, then we will approximately get the answer as 4 into 10 raised by minus 9 meter over second. So let's move on to the next example. Estimate how long the line would be if all the people on the earth were to hold hands in a straight line. Calculate how many times it would wrap around the earth at the equator. The radius of the earth is about 6 into 10 raised by 6 meter. Assume that the person has his or her hand stretched out to a distance of 1.5 meters. So we have to assume like the distance of 1.5 meter, and that the population of earth is 7 into 10 raised by 9 people. Really, uh, this is just a fair estimate, but now the population has increased so much. Then the length of the line of the people would be 7 into 10 raised by 9 into 1.5 meters, and equal to 10 raised by 10 meter. The circumference of the earth is 2 pi r, which is 6 into 10 raised by 6, which is approximately this much. And so the line would wrap 10 raised by 10 over 4 into 10 raised by 7, which is approximately 250 times around the equator. And then estimate how many apples. The next question is estimate how many apples it takes to have a combined mass equal to that of the ordinary family car. So let's assume that an apple has a mass of 0.2 kg and a car has a mass of 1400 kg. Then the number of apples is 1400 over 0.2, which equals 7 into 10 raised to power 3. And now the next question. Estimate the time it takes the light to travel at the Earth from the Sun. The Earth to Sun distance is 1.5 into 10 raised by 11 meters, and the time taken is distance over speed. Okay, so the distance is 1.5 into 10 raised by 11 over 3 into 10 raised by 8, which is 0.5 into 10 raised by 4 equals 500 seconds, which equals 8 minutes. These were quite interesting questions. Please let me know in the comment box. Uh, then here comes the significant figures. The number of digits used to express a number carries information about how precisely the number is known. A stopwatch reading of 3.2 seconds, which has two significant figures. How it is two significant figures? Let me tell you. 3.2 because it has 3.2, it has two significant figures, and is less precise than a reading of 3.23. It has three significant figures. If it would be 3.2 and after that two zeros, 3.200, then also it would have two significant figures here, because the zeros at the end and in the starting does not count. If it would be 003.2, then also it will be two significant figures. Okay, then let's read. If you are told what your salary is going to be, would what you would like that the number to be known as precisely as possible. It is less satisfying to be told that your salary will be about 1,000, which is 1,000. Look here, it has one significant figure because zeros at the end or zeros at the start do not count. So it has just one significant figure, euro a month, compared to a salary of about 1,250, which has three significant figures. Here, the zero at the end does not count, so just the three significant figures, euro a month. Not because 1,250 is larger than 1,000, but because the number of about 1,000 could mean anything. Like 1,000 could mean anything, like it may varying from a low of 500 to a high of 1,500. Who knows? And you could be lucky and get the 1,500, but you cannot be sure with a salary of about 1 to 1,250. Your actual salary could be anything from 1,200 to 1,300, so you have pretty good idea of what it will be. So then the question here arises is how to find the number of significant figures in number is illustrated in the table we are going to see. Don't worry if anyone doesn't understand, let's uh, read and I will explain it to you. So here I have the table, like here we have some numbers and the we will find out the significant figures. So number is 504, which has three significant figures, like zero in between counts, but the zero at the end does not count. So it will be three significant figures in an integer. All digits count if the last digit is not zero. This is the reason for this. So scientific notation is 5.04 into 10 is power 2. We can donate it scientifically by this notation, and the next number is 608000, which has three significant figures, like the zeros at the end do not count. So zeros at the end of an integer do not count. So 6.08 into 10 raised by 5 is the scientific notation we have here. And then we have another number 200, which has the number of significant figure 1 because the zeros at the end do not count. Zeros at the end of an integer do not count, the reason. And the scientific notation is 2 into 10 raised to power 2. And here comes our next number, which is 0.000305. Okay, so number of significant figures would be 3 because zeros in the front do not count. And the scientific notation we can also note it in this form, 3.05 into 10 to the power minus 4. And the next number we have here is 0.005900, which has the number of significant figures 4 because zeros in the front and in the end do not count, so we will leave all these zeros and just this number 59. No, zeros at the end of the decimal count, those in front do not. So zeros at the end here is like zeros like 5900 after. So because after the decimal, if we have the number like 5900, so these four, we have four significant figures. If we had like 0.00404, then we have three significant figures. Like here we have 0.000305, we have three significant figures. Okay, so here we can denote it scientifically by 5.900 into 10 raised by minus 3. And so, yeah, I think now it's the concept of significant figures is clear to everyone here. If you still have any query, then please let me know. You can ask me in the comment box. And the scientific notation means writing a number in the form a into 10 raised power b, where a is the decimal such that 1 is smaller or equal to a, or here 10 is greater than a, and the b is positive or the negative integer. The number of significant figures in a is the number of significant figures in the number. So in the multiplication or the division, or in the raising a number to a power or taking a root, the result must have as many significant figures as least precisely known number entering the calculation. So if we have the greater number of digits, so it's good and it's more precise, so we can get the accurate answer. So we have, we have that 23 into 578, which equals 13,294, which equals 1.3 into 10 raised power 4, which has two significant figures here. But here it has 23 as two significant figure and three significant figures are here. So we just have to see the least number of significant figures, which are shown in the red color here. So after that, here also we should have the least number of significant figures, remember. So like here we have 6.244, which has four significant figures, and the 1.25, it has three significant figures. So the denominator has the less number of significant figures than the numerator, so which equals 4.9952 and so on, and which approximately equals to 5.00 into 10 raised power 0, which is 5.00, and it has, we have to show it in three significant figures because the three significant figures is the lowest number of figures here. Yeah. So here next example is like 12.3 raised to power 3, which equals 1860.867 and so on, which approximately equals to 1.86 into 10 raised to power 3, which has three significant figures like this. So, and the next example is root over 58,900 equals 242.6932 and so on. So it will also have the three significant figures. It cannot have four significant figure or five significant figure or not less than three. Just the same significant figure as we have here. We should also get the same significant figures here. I hope you are able to understand this. And in addition and subtracting, the number of decimal digits in the answer must be equal to the least number of decimal places in the number added or the subtracted. So as I have said before, you should that it must be equal to the least number of decimal places in the number. So let's move on. 3.2 plus, if we add both of them, plus 4.1, so which one has least significant figure? Like it has, we are looking at the decimal places, like it is like before two decimal places, and 4.1 it's like before one decimal place, and so answer should be just in one decimal place, like the least digit as we have read here. So it would be 7.3, the least number of decimal places shown in the red. And now 12.367 minus, we are taking out the difference, 3.15 equals 9.217, which approximately equals to 9.22, which has two decimal places, as here we have two decimal places. We here, but here we have three decimal, so we have to look at the least decimal place every time. And now use the rules for rounding when writing values to the correct number of decimal places or the significant figures. For example, the number 542.48 equals 5.4248 into 10 raised to power 2 rounded to 2, 3, and 4 significant figures. It becomes, let's see, 5.4 this, and 248 into 10 raised to power 2. Then if we divide them and calculate the value, so No, this is not the divide symbol. This is the oh, we are okay. So we have to see the significant figures and round off them to the least number of significant figures. So here we have this line is just to show the difference of the digits, okay, not the division symbol. So 5.4248 into 10 raised power 2 is 5.4 into 10 raised power 2. We have to leave the final digit in the number of significant figures like here. So it's rounded to two significant figures, and here it's rounded to three significant figures, and so on. This is a special rule for rounding when the last digit to be dropped is 5, and it is followed only by zeros or not followed by any other digit. Yeah, so this is the odd even rounding rule. For example, consider the number, let's consider this number 3.2500000, and so on, where the zero continue indefinitely. How does this number round to two significant figures? How does this round to two significant figures? Because the digit before the 5 is even, we do not round up, so 3.25000 so on becomes 3.2. Okay, so 2 is even, so that's why. But 3.35000 rounds up to 3.4. Because why? I think now you can understand this. 3.4 because the digit before the 5 is odd. Yes. And so, number of nature of science. Early work on the electricity and magnetism was hampered by the use of different systems of units in different parts of the world. Uh, Scientists realized they needed to have a common system of units in order to learn from each other's work and reproduce the experimental results described by others. Following an international review of the units that began in 1948, the SI system was introduced in 1960. So early works were going on electricity and magnetism when they were hampered by use of different system of the units. Like they had a great confusion. Like in different parts of the world, they use different units, and so that's why they had to take one SI system, one such system, so that they can take it more precisely and correctly. So at the time there were six base units at the time. In 1971, the mole was added. So the new quantity mole was added in 1971, bringing the number of base units to the seven in use today. So today we have seven base units. We have read today. As the instruments used to measure quantities have developed, the definitions of standard units have been refined to reflect the greater precision possible. Using the transition of cesium-133 atom to measure time has meant that smaller intervals of time can be measured accurately. And the SI system continues to evolve to meet the demands of the scientists across the world. Increasing precision in measurement allows scientists to notice smaller differences between results, but there is always uncertainty. In any experimental result, there are no exact answers. There are many uncertainties, and that we are going to learn in our next video. So that's all for today, and thanks for watching. And if you like our video, then please hit the like button and subscribe our video. And goodbye, have a nice day.